To understand grand unified theories, one quickly encounters concepts such as Lie algebras, roots, Cartan matrices, and Dynkin diagrams. These ideas are often introduced separately, making it difficult to see how they fit together. The purpose of this video is to present the shortest path connecting them. We will start from a Lie algebra and follow a sequence of ideas that leads naturally to Dynkin diagrams. Our roadmap flows from a Lie algebra to the Cartan subalgebra to roots, then to simple roots, through the Cartan matrix, and finally to the Dynkin diagram. A Lie group describes a continuous symmetry. Rotations provide a familiar example. A rotation can be changed continuously, and this continuous structure is precisely what makes rotations a Lie group. Rather than studying the entire group directly, it is often more useful to focus on transformations infinitesimally close to the identity. Near the identity, a group element can be written using an exponential map, where T is called a generator. The generators contain the local information of the symmetry. But how do we learn how different generators interact with one another? When two infinitesimal transformations are combined, their generators do not necessarily commute. In fact, multiplying two infinitesimal transformations naturally produces terms involving the commutator of TA and TB. This can be seen from the Baker-Campbell-Hausdorff formula. Closure of the algebra then requires the commutator to be expressible as a linear combination of the generators themselves, written as follows. Where the numbers f, a, b, c are called structure constants. These commutation relations define a Lie algebra. For most applications in particle physics, the Lie algebra is the main object of interest. The next question is how to organize the generators of a Lie algebra. We begin by selecting the largest possible set of generators that commute with one another. These generators form the Cartan subalgebra. If there are independent commuting generators, the algebra is said to have rank R. Let us look at a few examples to see how this works. SU2 has three generators, T1, T2, and T3. Their commutators are non-zero, so no two independent generators commute. The largest commuting set therefore contains only one generator, meaning the rank of SU2 is 1. The algebra SU3 contains 8 generators. Among them, exactly two independent generators can be chosen to commute with one another. Therefore, the rank of SU3 is 2. For orthogonal groups, the rank is given by taking the floor function of n over 2. Following this rule, the rank of SO10 is exactly 5. This number, 5, will later reappear as the number of nodes in the Dynkin diagram of SO10. Once the Cartan generators have been chosen, we can study how all remaining generators behave with respect to them. With a suitable choice of basis, the commutators take a very specific form. Here, the generators Hi belong to the Cartan subalgebra, while E alpha denotes the remaining generators. The numbers alpha, which form a vector, are called roots. A root can therefore be viewed as a vector that records how a specific generator responds to the Cartan generators. The complete collection of these vectors is called the root system. Different Lie algebras have different root systems, and much of their physical structure is encoded in these vectors. Roots always occur in pairs. If alpha is a root, then minus alpha is also a root. We therefore choose one half of the roots and call them positive roots. Among the positive roots, some can be written as sums of other positive roots. Those are not fundamental. The positive roots that cannot be decomposed in this way are called simple roots. For example, the algebra SU3 has three positive roots, alpha 1, alpha 2, and alpha 1 plus alpha 2. Only the first two are simple roots. The third is obtained simply by adding them together. A fundamental theorem states that the number of simple roots is always equal to the rank of the algebra. Thus, a rank 5 algebra possesses exactly 5 simple roots. For SO10, whose rank is 5, there are therefore exactly 5 simple roots. The next step is to study the geometric relations among these simple roots. The key quantity is their inner product. These relations are encoded in the Cartan matrix, defined by Aij. For SU3, the Cartan matrix is a 2x2 matrix that looks like this. The Cartan matrix records the relative lengths and angles of the simple roots. In principle, it contains all the information needed to reconstruct the entire root system. However, the exact same information can be displayed much more visually. Instead of writing a matrix, we draw a graph. Each simple root becomes a node, and the geometric relations between the roots become lines connecting those nodes. The result is called a Dynkin diagram. For example, the Dynkin diagram of SU3 consists of two nodes connected by a single line. This diagram is mathematically called A2. More generally, we have a beautiful correspondence between classical Lie groups and these geometric diagrams. Since SO10 can be written as SO, 2 times 5, its Dynkin diagram belongs to the D series. Because its rank is 5, its Dynkin type is D5. Its Dynkin diagram contains 5 nodes, arranged with a characteristic symmetric split at the end. This is the foundational Dynkin diagram that underlies the group SO10. We can now summarize the overall picture. A Lie algebra contains a maximal commuting subalgebra called the Cartan subalgebra. The Cartan generators define the roots. Among the roots, the simple roots contain all essential information. Their geometric relations are encoded in the Cartan matrix and represented graphically by a Dynkin diagram. This is why Dynkin diagrams beautifully classify Lie algebras. At the same time, Dynkin diagrams alone do not yet explain the familiar particle representations of SO10, such as the 10, 16, 45, 120, or 126. To understand those representations, we need a second set of vectors known as weights. Roots classify Lie algebras. Weights classify representations. And that is exactly where Dynkin labels such as 10000, 00010, and 00001 enter the story. That will be our next step.